The sun is not a quiet ball of light. It's a dynamic, explosive force, the very heart of our solar system. And it has a profound influence on Earth in ways that go far beyond providing daylight and warmth. Welcome to the world of solar flares, coronal mass ejection, CMO, and space weather. Phenomena that not only shape conditions in space, but directly affect life and technology on Earth. At the core of this activity is the sun's magnetic field. Twisting, tangling, and reconfiguring constantly, this magnetic energy sometimes becomes unstable. When it does, it can release massive bursts of radiation and particles into space, what we call solar flares. These flares can be immensely powerful. In mere minutes, they can unleash the energy equivalent of billions of hydrogen bombs. Most solar flares occur in active regions near sunspots, dark patches on the solar surface caused by magnetic disturbances. Occasionally, a solar flare is accompanied by a coronal mass ejection, a massive bubble of solar plasma and magnetic field that is hurled into space. If a CME is aimed toward Earth, it can reach us in a few days and create significant space weather effects. But what exactly is space weather? Unlike Earth's weather, which involves wind, rain, and temperature, space weather is a set of electromagnetic and particle conditions influenced by solar activity. It impacts satellites, power grids, communications, and even the health of astronauts. When a CME slams into Earth's magnetosphere, the magnetic bubble surrounding our planet, it can compress and disturb it. This interaction generates geomagnetic storms, which cause beautiful auroras near the poles, but can also damage electrical systems. In 1989, a powerful geomagnetic storm caused by a CME knocked out power across Quebec, Canada, leaving millions in the dark for hours. In 2003, during the Halloween storms, dozens of satellites were disrupted. Airline flights were rerouted, and astronauts on the ISS were warned to seek shelter. The most powerful solar storm ever recorded, the Carrington Event of 1859, caused telegraph systems to spark and fail. If a similar event occurred today, with our modern reliance on electronics and global connectivity, it could be catastrophic. That's why monitoring the sun is more important than ever. Organizations like NASA, ESA, and NOAA maintain fleets of space observatories that keep a constant eye on our star. The Solar Dynamics Observatory, SDO, SOHO, and Parker Solar Probe provide real-time data on solar conditions, helping predict solar storms and alert power companies and satellite operators in advance. Understanding space weather isn't just about avoiding disaster. It's also about exploration. As we send humans back to the Moon and eventually to Mars, we must account for the radiation risks posed by solar activity. Unlike Earth, other worlds lack strong magnetic shielding, making astronauts more vulnerable to solar radiation. Even airline crews flying at high altitudes near the poles during a solar storm can receive increased radiation doses. GPS signals can be disrupted. Shortwave radio communications, critical for military and maritime operations, can go dark. And yet, there's beauty in this danger. When solar particles collide with Earth's upper atmosphere, they create the aurora borealis and aurora australis, shimmering curtains of green, red, and purple light dancing across the polar skies. These northern and southern lights are not only spectacular, but living proof that we're constantly interacting with the sun. They're a visual reminder that space is not empty. It's alive. It's connected. The sun operates in cycles, most notably the 11-year solar cycle, which governs the frequency of sunspots and solar storms. We are now entering solar cycle 25, expected to peak around 2025. Scientists anticipate increased solar activity, which could bring both stunning auroras and significant space weather risks. Preparation is key. The more we understand the sun, the better we can predict its behavior. Researchers are developing advanced models to simulate the solar corona and magnetic field. Missions like Parker's Solar Probe, which is flying closer to the Sun than any spacecraft in history, are revolutionizing our understanding of solar physics. Meanwhile, engineers are hardening satellites against radiation. Airlines are updating flight plans based on space weather forecasts, and power companies are building resilience into their grids. It's a coordinated effort, blending astrophysics, engineering, atmospheric science, and public safety. At Infinity Beyond, we believe knowledge is protection. That's why we share the latest insights into solar activity, geomagnetic forecasts, and what it all means for our future in space. Because ultimately, the Sun isn't just out there, it's part of us. Its energy sustains life. Its outbursts shape our skies. Its storms challenge our technology and stretch our understanding. And as we venture farther into the cosmos, the Sun will remain both a source of wonder and a force to be reckoned with.